Assalamualaikum warahmatullahi wabarakatuh and selamat sejahtera to Puan Izzadura binti Mustafa, which is our lecturer. So today we'll be presenting about FIR, which is finite impulse response filter. So we focus for designing FIR filter with window technique for the application. So before that, I'm going to introduce myself. My name is Nur Zahira binti Zulkifli. So I'm going to present for part introduction. So this is our group members. Okay, so for the introduction, an FIR filter is a filter with no feedback in its equation. This can be an advantage because it makes an FIR filter inherently stable. Another advantage of FIR filter is the fact that they can produce linear phases.
Assalamualaikum, my name is Nurul Afifah binti Alias with the metric number of B0820102225. So today I will continue my presentation for our assignment, which is the objective. Before that, as we know, FIR filter, which is finite impulse response, has an impulse response that settles to zero in a finite time, while IIR filter, which is infinite impulse response, is recursive filter that use the current and previous input and previous output to compute the output. So first of the objective is to understand the basic concepts and working principles of the FIR and IIR filter. Next, it is to understand the structure of the FIR and IIR filter. It is also to understand the concepts of certain basic FIR and IIR filter design techniques. And then lastly, it is to acquire the capability of designing FIR and IIR filters to meet certain filtering requirements. So the main objective of a FIR filter is to implement a linear time invariant system with a finite number of coefficients for application requiring a linear phase response. While for the IIR filter is to implement a linear time invariant system with an infinite number of coefficients for application requiring a sharp cut-off step roll-off in the frequency response. So that's for the objective for our assignment.
I'm going to show you the MATLAB coding. So here's the coding. As we did in Lab 4, so these are the coding for Z-plan. So there are 4 systems, which is system 1, 2, and 3, and also 4. So for the system 1, B1 is a coefficient numerator of a transfer function system. So there are 4 numerator, which is 0.1, 0.4, 0.4, and also 0.1. So these are the coefficient of transfer function system 1 for a denominator. So next will be the root number for B1. So we're using the root function. Also for the denominator for A1, we're also using the root function. So here is the frequency function for B1, A1, and also N. The N is as stated here, 1024. Same goes as to system 2, 3, and also system 4. Okay. So as you can see here for the system 3, the numerator will be 0.25, negative 0.25, 0.25, and so negative 0.25. While for system 4, 1, 0, 2.618, 0, 2.618, 0, and 1. So the next part, we're going to plot the graph So we use the command for subplot 4 to 1 to plot the graph for transfer function. So we plot by using W1 divided by pi times H1. The title will be magnitude response H1. The X level will be normalized frequency while the Y level for H1. So we have to plot another graph for Z plan for pole and 0. So we subplot to 4 to 2 root num 1, root 1 num, and also root 1 denominator. So the title will be Z-plane plot H1. Same goes as the system 2, 3, and system 4. So that's all for me. I will pass to my other group members.
So next I will show you the result of the output that we have configured from the coding. Before that, I will show you from the MATLAB that we are using to configure the coding to get the output. So I will run this coding. So the output that we get from the coding is there are two parts of the output, which are magnetic response and Z-plane fluid. The magnetic response, which is a response of a filter to measure of its output level at different frequencies that represented in dB and determined by its transfer function. While for the Z-plane fluid, it used to represent the poles and zeros of a filter transfer function, which is determines its frequency response and stability. So the result is given by the part from the H1, H2, H3 and H4 for the both part. This is the output for the magnetic response, which is X level is normalized frequency, and for the Y level is H1 or H2 or H3 and or H4. So they are using the subplot by its formula, which is already configured from the coding. So for the H1, we will get the low pass filter. For the H2, we will get the band pass filter. H3 will get the high pass filter, and lastly H4 will get the reject band filter. So all the graphs are related to the value that has been set in the coding for the H1, H2, H3 and H4. So this is for H1, this is for H2, this is for H3 and this is for H4. Next for the Z-plane fluid, which also for the H1, H2, H3 and H4. So Z-plane also has a X level, which is real part, and Y level, which is imaginary part. So they are using subplot, which is using the root function of the numerator and denominator. In this output, they are having a zero symbol and X symbol. The zero symbol is the symbol for the zeros, while the X symbol is the symbol for the poles. So this is same as the magnetic response, which they are have H1, H2, H3 and H4. So that's all from my part. I will pass to the next presenter to continue the presentation. Thank you.
Assalamualaikum. My name is Mama Irfan bin Daud. My number matrix is B0820101190. So today I will explain about the application. So as madam can see, the title is Designing FIR Filter with Windowing Technique. So what is windowing? So basically windowing is the process of processing and analyzing a small subset of the larger dataset. So the simplest technique, the rectangular window, simply stop the dataset before and after the window without changing the content of the window. So to more understand, I will show the coding in MATLAB. Okay, this is my coding for the window function. So first of all, I will put the variable n for the filter response. Next, for the FP is the passband frequency. For the Fs is the stop band frequency, and F for the sampling frequency. So this value I put a number, random number. So this variable and function for WP and WS is the for convert this to the radian per second. So this is the limit of the frequency. That means to convert cut off frequency to radian, this function. So next, this is the list of the window function. So the first window is the rectangular window. Next, the bullet window or triangular window. Then this is a Hamming window. This is the Henning window, and lastly, this is for Kaiser window. So after we write this function of window, we used to this is the cutoff frequency to radian formula. So next, B, go to FIR and omega m window. So this is FIR is the window based FIR design. So this is the function. So this is the coefficient that include n, omega n, and window. So next, same, the function is same. So the difference is this is low pass filter and this is the high pass filter. So we put the high for the high pass. So next, for the bracket H and W, this is for to form a frequency response for vector H, and this is to corresponding angular frequency vector for omega. So frequency Z B1. So frequency Z, this is mean frequency response of the digital filter. So after we do this, we can subplot for the graph. So the first subplot, we plot omega per pi because this is the radian formula, and this is 20 times log absolute H. This is for the decibel formula or dB. So this is the basic S label for X axis, Y label for Y axis. This is for the title. So the next subplot is we use radian and we use the angle formula. So next, X axis, Y axis, and title. So I will run this coding to show the low pass first. So this is the output or result for the low pass. That this value start with 0 because this is FIR filter that has zeros, then not have a pulse. So same, this is magnetic response, this is a phase response. So next I will show for the high pass. So we just uncomment the coding or the line. So we run. So this is the graph for the high pass. As madam can see, is we can see is as a mirror. For low pass, it start from left. For the high pass, start the zero is start from right. So for the output of rectangular, triangular, ballot, Hamming, Henning, and Kaiser, my friend will show for the next part. So that's all for my part. Thank you.
Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Today I will explain the output of this all command window, Boxcar, Bartlett, Hamming, Henning, and Kaiser. This command, this command for low pass filter, and this one for high pass filter. Okay, at first I will do for the rectangular window first, boxcar command for the low pass filter. Alright, this is the output for the low pass filter. If I want to change for high pass filter, I just add a comment here, change the comment here, and put it up. Alright, just like that, and run simulation. Okay, this is for the output for rectangular window for the high pass filter. Boxcar function is any function which is 0 over the entire real line except for a signal interval where it's equal to a constant a. The Boxcar function can be expressed in terms of the uniform distribution. So next I will do for Bartlett command, which is triangular window. If I want to change, just change the comment here, put it down, and I will do the low pass first, and the second one high pass. Okay, wait. Like run section. And this is the output I get. This is the output for low pass filter for triangular window, and this is for the high pass. Wait, a little bit slow. Okay, this is the output for the high pass filter for triangular window. I'm using this command Bartlett. The Bartlett window is very similar to a triangular window, except the endpoint are at the 0. It is often used in signal processing for tapering signal without generating too much ripple in the frequency domain. Okay, next one I will do for the Hamming. just change the comment here and run section, run section. Okay, this is the output for Hamming window for the low pass filter, and this is for the high pass. Allah Rabbi. Okay, this is for the high pass filter for Hamming. The Hamming window is a taper form by using a rest cosine with non-zero endpoint optims to minimize the nearest rise slope. Number of point in the output window. If 0 or less, an empty array is returned. When true, generate a symmetry window for use in filter design. So I will do Hamming. Oh, sorry, it crashed again. I will run section again. Okay, this is for the Hamming window. This is for the Hamming window for the low pass filter, and the next one is high filter. I just add some comment here and run section. Oh Rabbi, it crashed again. Wait, I need to close it first. Alright, this is the output for Hamming window for low pass filter. Oh sorry, high pass filter. And the last one is Kaiser window. I'll close first, run section. Astaghfirullahaladzim. Okay, this is the output for Kaiser window for the low pass filter, and the next one is high. I will do the high pass filter. Okay, this is for output for the high pass filter. Kaiser Kaiser window. It is one parameter family of window function used in finite impulse response filter design and spherical analysis. The Kaiser window approximates the DPSS window, which maximizes the energy concentration in the main lobe but which is difficult to compute. So the conclusion, this is all the window design filter. If we want to use, this is all the command: window Boxcar, Bartlett, Henning, and Kaiser. This is the command for low pass and high pass. Also, we have 5 example of filter here if we want to use. So we have 5 example design filter. Thank you.